now that we've seen the proof of the first part of the fundamental theorem of calculus, let's see how we can use it to evaluate definite integrals. So for this first one here, we want to evaluate the integral from 3 to 8 of 2. We've already seen the geometric interpretation of that as the area of a rectangle. We could go through and use the definition, but since we're told that we just need to evaluate it, let's see how we could use the fundamental theorem of calculus. So the function f of x equals 2 is certainly going to be continuous over the interval from 3 to 8. I just need to come up with an antiderivative. So certainly 2x has derivative 2. You could, of course, put 2x plus any constant, but typically we just find the simplest antiderivative, thinking about the additive constant being 0. And the way we express this is we put our evaluation bar and we put the values that we want to evaluate it on the bottom and top there. So this says take 2 times 8 and subtract 2 times 3. So we're going to take 16 minus 6 and end up with 10. For this next one, again, I have a continuous function over the interval from 1 to 4. I need to find an antiderivative. So the antiderivative of 2 that we just talked about was 2x. And then likewise, I can subtract an antiderivative of x squared over 2. And we want to evaluate this from x equals 1 to 4. So we're going to plug in 4 first. So 2 times 4 minus 4 squared over 2. And then we're going to subtract what we get when we plug in 1. So we can see here I'm going to get 2 times 4 is 8, minus we have 4 squared over 2, which is also 8. And we're subtracting, and I'll say it's important to really keep track of your negative signs. So this next negative is distributed throughout. So I have 2 minus 1/2. And so we're going to end up with here negative 3/2. For this next one here, the function sine of x is, again, continuous from 0 to pi. The antiderivative of sine of x is negative cosine of x. And we're evaluating that from x equals 0 to x equals pi. So we're going to get negative cosine of pi minus a negative cosine of 0. Cosine of pi is negative 1, but we're multiplying it by negative 1. So we have to be careful. That's going to be a positive 1. And then minus, well, cosine of 0 is 1. Negative cosine of 0 is negative 1. So all of these minus signs are just going to give me a positive 1 plus another 1. And so we'll get 2. And something like this next one here, this is a little bit more complicated. This is not typically something we would necessarily right off the bat have an antiderivative for. One of the things that I think about with exponential functions is that we know that the derivative of e to the x is itself. So something like this, you could really implement a kind of a guess and check at this point. So what I mean by that is, suppose we guessed that the antiderivative was simply e to the minus 2x. The check part here is, well, if I take the derivative of my guess, do I end up with my integrand? And of course, we don't, because the chain rule brings out a minus 2. And we don't want this minus 2 there, so we can divide our guess by negative 2. So we put this negative 1/2 out front. So this has the appropriate antiderivative. What I will say is a few things here. What we just demonstrated here would really work for any constant in place of negative 2. So if I have e to the cx, the antiderivative is going to be 1 over c e to the cx. And the other thing I'll kind of reference here is that we'll see an integration technique in a little bit that actually will formalize kind of where that constant comes from. But at this point, just being able to handle a constant multiple of the variable up in that exponent is sufficient. So that's our antiderivative. We're evaluating it from x equals 0 to x equals 1. So I'm going to get negative 1/2 e to the minus 2 minus a negative 1/2 e to the 0, which is 1. And so we're going to get negative 1/2 e to the minus 2 plus 1. Oops, I should say plus 1/2. So being careful about simplification there. So that's my antiderivative for that. And so this is just a little look into how we can use this theorem. And then you can imagine getting a lot of practice with a lot of different specific definite integrals. So what I want to look at now is just to be a little bit cautious at this point, especially in comparison to having to use the definition to evaluate a definite integral. This seems very, very simple and like it's kind of the answer to all questions that we're looking for. But it's not always going to be directly helpful. So one thing I do want to stress is the fact that we required f to be continuous, the integrand, when we talked about the statement of FTC. So if my function is not continuous over the entire interval that we're integrating, so if there exists even just one discontinuity, then we can't simply apply this theorem. So to illustrate this, I'll point out an example is if we were to integrate from -1 to 1, 1 over x squared, right? That's x to the minus 2. Well, an antiderivative of x to the minus 2 is certainly negative x to the minus 1. So, right, that's negative 1 over x. And if I evaluate it at these bounds, we're going to get negative 2. So, of course, if I'm working through that problem, that doesn't necessarily make me pause. I'm able to evaluate and get a number. But that's impossible that that could be the number based off of our interpretation so far, because let's think about the graph of 1 over x squared. Roughly, it's going to look like this. And we're talking about, whoops, this region. And of course, I can't look at the graph to quantify that, but what I can certainly tell is that that's not negative. Oops. Right, my answer was a negative 2, so I should expect to see negative area, and that's not the case there. So this isn't a contradiction of the theorem. The problem was that f of x has a discontinuity in this interval over which we were integrating. Oops. So in the interval from -1 to 1, specifically at x equals 0. So we wouldn't be able to use that. We're going to see later that this is an example of what we call an improper integral. So we will have ways to deal with that, but we can't simply just evaluate it at the bounds. We're going to have to do something more. And the other thing I'll point out here is we have to be able to find big f of x, right? Otherwise, this isn't going to be useful. This can be relatively innocuous, that maybe the way that we do that requires a more sophisticated technique, which we'll cover later, use substitution and integration by parts. But it can be worse than that, in that there exist examples where it's impossible to find a big F in terms of what we call elementary functions. So the example I'll put here is this. So e to the x squared is a classic example of a function where you won't be able to find an antiderivative written in terms of nice functions, e to the x, sine, cosine, polynomials, anything like that. So often people, when first looking at this, think that they do know an antiderivative. But if you were to try to, if you think you have one, take the derivative of it, you'll never be able to get back to e to the x squared. That means that we can't use FTC to evaluate this integral because we don't have a big F. The computers can numerically evaluate definite integrals involving this. And so these are still show up in applications, but it's worth noting that we can come across some of these things where FTC is not going to allow us to really carry the problem through just on that alone.